Okay, we can get going. Any questions from anyone before I get started? About final projects, final reports, logistics, anything like that? Okay, I'll just remind you that final demos are next week. I trust that probably everybody has already signed up for a demo, for a time slot to demo, but if not, you want to do that like now. Still need to? Okay, that's fine. Okay, so unless there's any questions, my plan for today was to, like I said, or like I've said before, once we get into final project season, it's sort of special topic stuff, things that I think are of broad relevance or interest to folks. So what I thought we'd talk about today is the CAN bus. I want to talk about it for a few reasons. One of those reasons is that there is, in fact, a group that's making use of this for their final projects, and so it's of some relevance to, some immediate relevance to folks in this class. But even for those of you for whom this is not of immediate relevance, I will bet that if you choose to make a career in embedded systems, you bump into the CAN bus at some point, particularly if you choose to go do embedded systems at any kind of a vehicle company. As I'll talk about, the CAN bus, Controller Area Network is what CAN stands for. It was designed for vehicles, and it remains extremely ubiquitous in vehicles. By vehicles, I mean things like cars, forklifts, to my knowledge, airplanes, probably submarines, probably some spacecraft, though I'm not sure. But in any case, you find these in a lot of vehicles because it has some properties that lend itself really nicely to that. So I want to talk about it for that reason also, because I'll bet that you bump into this if you choose to make a career of doing this stuff. Also, it's just really interesting. It's sort of, you could, if you draw a comparison to things like I2C or SPI or these other mechanisms by which we can exchange information among a bunch of different sort of nodes in a network, this has some properties that are very different from those other ones that I think are really quite interesting. And also, it gives me yet another excuse to talk a little bit about these PIO coprocessors and a little bit more about DMA. And so for all those reasons, I thought it would be an interesting thing to cover. And so ultimately, what I would like to come back to is some topics on this webpage, which is linked up on the course webpage, that describes a CAN driver implementation in PIO. But before we go to this, I thought we'd spend some time talking in the abstract about how this protocol works. And I was going to put together some slides for this, but in fact, the Wikipedia article has just some nice diagrams that I thought we'd use directly. So before I get into this, let me say some general properties of the CAN bus. The data channel for the CAN bus is differential. So that is to say, rather than having a single data line on which we encode bits by setting the voltage on that line high or low, instead on the CAN bus there are two data lines, and to encode a bit, we set one high and the other low, and if we want to encode the opposite polarity bit, a 0 instead of a 1, we swap them. The other one becomes high and the other one becomes low. And so there is still only a single data channel. It's just the case that that data channel is composed of two differential lines that we control simultaneously. You see this, incidentally, in some other kinds of communication channels. Ethernet would be an example. The reason to have a differential data line like this is for noise mitigation. Instead of looking at the absolute voltage on a data line, what we're looking at instead is the difference in voltage between these two things, which helps with noise rejection. But, as we'll discuss, the CAN bus, the connection between the nodes on the CAN bus is only that differential data line. There does not exist a clock line. There does not exist any chip select. And even so, a very, very large number of different nodes on such a network can communicate with one another and exchange information. It raises some interesting questions. How do they not talk over one another, right? What is the mechanism by which one node says, I have control of the bus right now, please don't anybody else talk? Without a chip select line, how does some other node know that it's being spoken to, right? And the mechanism by which that actually works for CAN is I think, really clever and really interesting. So if we scroll down here a little bit, I want to talk specifically about specifically about, let's see, let's start down here at the packet format. If you consider a CAN packet, you know, the ones and zeros that compose a message that might get put onto the CAN bus, it has a bunch of different sections in it. Okay, generally speaking, it's composed of the following. Every one of these CAN packets will start with a start of frame indicator, which looks like a logical 0 on the CAN bus. The reason for this is this whole system is organized such that there exists a dominant bit and a recessive bit. In the event that nobody is communicating on the CAN bus, then by default, the high and low differential lines are pulled to such an orientation that it looks like there's a logical 1 living on the CAN bus. Basically, it gets pulled high, so to speak. Any node on the network, however, has the ability to pull the data line low. This is very sort of analogous to I2C with its pull-up resistors, right? You might recall from our discussion of I2C that those pull-up resistors mean that when nobody's communicating, the data line is pulled high. A similar thing happens here. When nobody's communicating, the CAN bus is pulled high, logically high, and then when somebody wants to communicate, it pulls the line low. So the verbiage that you see used to describe that relationship between ones and zeros on the CAN bus is that the 1 is recessive and the 0 is dominant. A 0 can overpower a 1 because the line is not driven to a 1, it's pulled to a 1, but it's driven to a 0. And as we'll see, the communication method here takes advantage of that fact in an interesting way. But in any case, each of these packets starts with a start of frame buffer, which is a 0, right? It pulls the data line low, differential data lines low, to indicate that a packet is about to appear. That is generally followed by an identifier. The identifier, you could think about it as being the name of the device that is doing the communication. Alternatively, in some of these packets, or in some of these buses, it's used as a way to prioritize one message over another message. As we'll see in just a moment, it's this section of the packet, this identifier, that is used for arbitration among different nodes on the network. So if two different nodes start to speak simultaneously, they come to a decision about who sort of wins control of the network by way of this identifier. And so you could imagine if you wanted for the various nodes in your network to have different priority levels, then you might give them identifications that enforce a certain hierarchy of priorities, so that if device A wants to speak and device B starts to speak at the same time, device A might win over device B, or vice versa. Alternatively, if you want to have packet level prioritization, so that any device can have a packet take precedent over other packets that might be trying to be communicated at the same time, you could use this for that reason as well. And like I said, I'm waving my hands at that for just a moment, but I want to revisit that and talk about exactly how that works. There's generally a 1-bit remote transition request. This is how we indicate to the device to whom is being communicated whether we are sending it data or requesting data from it. There's optionally an identifier extension bit. There's a extension of this CAN packet protocol that allows for you to extend that identifier field, in principle to allow for more levels of priority or perhaps more nodes on your CAN bus. There's a reserve bit. There is, of course, the data here, preceded by a data length code. This indicates how many bytes the payload's going to be. This is, in fact, the data payload. That's followed by a checksum, computed on everything that precedes it, followed by a checksum delimiter, a 1. This is followed by an ACK slot. It is the case sometimes, this is the sender of the packet will send a 1 here, and sometimes it's the case that these packets will be set up such that the destination for that packet, the destination device, will pull the ACK slot low to indicate to the sender that the packet has been received, right? So the sender allows for the data line to be pulled high, and then sometimes it's the case on these buses that the device that received that packet will actively pull it low. This is very similar to, we saw a similar organization when in our discussion of I2C. You may recall, we were talking specifically about communicating with the IMU. There was another ACK there, okay? And in that ACK, the sending device allowed for the I2C lines to be pulled high, and in the event that the packet was successfully received, the other device would pull it low to indicate that it had received that packet. That exists here as well. There's an end of frame delimiter. This is just a sequence of 7 ones. And then between packets, there's a certain amount of bit time that must pass before the next packet arrives. Okay, so this is the structure. There's some interesting features to this structure, though. One of these features is, as I said, there does not exist a clock line here, which could present an issue, because without a clock line, it could be the case that the various nodes on your network become desynchronized, right? Even if you start them all simultaneously, their clocks are running at slightly different rates, and so after some amount of time, they might desync. And so we need some mechanism for resynchronizing the devices on our network. That mechanism, or resynchronization, occurs on every transition from a recessive bit to a dominant bit. So every time the data line transitions from 1 to 0, all the devices on the bus will resynchronize to that transition. This occurs, incidentally, there's a good diagram here. Let me see if I can find it. This occurs because a bit time to every device on the network lasts for some number of cycle times or whatever. You know, in the case, for instance, of the PIO implementation that we're going to look at, it is the case that every bit lasts 32 PIO instruction times. And every device on the network samples the bit at this point in the bit time. In the case of the PIO instructions, it samples at instruction number 24 of the 32 PIO instruction times that compose that bit. So everybody assumes that this is where the samples are occurring. So the resynchronization can happen because every device knows, you know, when the last transition occurred. And so when a transition occurs, it can count off the appropriate number of cycle times to sample at the correct point, and in effect, it resynchronizes with that transition. So this is how we prevent the various nodes from drifting around. But that implies that in order for resynchronization to occur, we need for our packets, we need to guarantee that our packets have a sufficient number of these bit transitions, 1s and 0s and so forth. And the protocol enforces that by way of an interesting strategy called bit stuffing. Let me just see here. Bit stuffing. The way that this works is when I want to send a packet, you know, say I want to send this packet up here, before I send it, the device that is sending that packet will bit stuff the packet. What that means is it's going to go through, and anywhere in the packet that it observes 5 consecutive identical bits, it will insert an opposite polarity bit into the packet. And so, for instance, here we see the start of frame indicator as a 0, and then we see 1, 2, 3, 4, 5, 6 zeros following that. The sending device, before sending the packet, it goes through and it counts. I see 1, 2, 3, 4, 5 zeros, and it inserts a 1. That 1 carries no information. That 1 only exists to force this bit transition so that we can do resynchronization among the various nodes in the network. So every time this happens, here's another event where there were 5 1s in a row, or 5 zeros in a row, it inserts a 1. Here's another one, it inserts a 1. In the event that it saw 5 1s in a row, it would insert a 0. So it's making certain that a sufficient number of bit transitions exist in this packet so that we can maintain synchronization. You may observe that the only place that this does not occur is here at the end of frame indicator, which is 1, 2, 3, 4, 5, 6, 7 1s. And so it is those 7 1s that indicate the end of the frame to everybody on this bus. And then, of course, this is followed by the amount of time between packets, which in this case is 3-bit times between packets before the next packet might appear on the bus. Okay, so our sending device composes this packet. Then before it sends it, it bit stuffs it. It is the responsibility of the receiving device to then go through this packet and remove all of the stuffed bits in order to recover the packet in its original unstuffed form. So there's sort of 2 extra steps here. There's an extra step involved in sending a canned packet, which is stuff that packet. And then there's an extra step involved in receiving it, which is unstuff it. But we know how to unstuff it because every time we observe 5 bits of the same polarity, we know that the next one will be opposite polarity, and we know that that one was inserted. So we remove it. So that kind of answers the question about synchronization, but the question that we have not answered here is how do we arbitrate among the various nodes? How do we decide which nodes get to talk when, which one gets control? As I alluded to earlier, that process occurs during the arbitration part of this packet. The way that this happens is, as I mentioned, ones are sort of the data sheets and the protocol description describes them as recessive. They're sort of default. They're undriven. When nobody's controlling the bus, it's at a 1. The zeros are dominant. So the way that arbitration occurs is we make an assumption that every device on this network has a different arbitration value, has a different name. Those names assign that device its priority level in the following way. Let's say I'm a device with a certain arbitration field. You're a device with a different arbitration field. We get unlucky, and we both try to start our transmission at exactly the same time. What will happen? Well, let's say that the first 3 bits of our arbitration fields are identical. Then what we're both going to do is let's say all of our first 3 bits are 0, 0, 0. Then both of us are going to put a 0 onto the bus, and then right after we do so, we're going to check the bus and see what bit is on the bus right now. Is it a 0? It is. I put that 0 on that bus, so far as I know, and so I continue to my next bit. And so do you, because you've also checked the bus, and you've also observed that there's a 0, the bit that you put on the bus, present on the bus. So we go to the next one. We do it again. We both put identical bits onto the bus. Let's suppose that both of our next bits are actually a 1, not a 0. Okay? So now we both put a 1 onto the bus. We both check the bus, and we both observe a 1. So we both still think that we are responsible for controlling the bus. Now let's suppose we both get to an arbitration field bit that differs from one another. Let's suppose that the next bit in my arbitration field is a 1, and the next bit in your arbitration field is a 0. Remember that the way that the physical layer of this is organized, zeros win over 1s. And so if 2 devices try to put 2 different bits out, if I try to put a 1 out and you try to put a 0 out, the bit that will actually appear on the bus is a 0. That's the one that wins. And so when we get to that first bit that disagrees, I am going to put the next bit of my arbitration field out, a 1 in my case. You are going to put the next bit of your arbitration field out, a 0 in your case. Then we're both going to check the value on the bus. What I am going to observe is that I put a 1 out, but actually the bit on the bus right now is a 0. And so what that tells me is that some device with higher priority than me, but with whom I just happened to share the first 3 bits of our arbitration field, is trying to communicate at the same time as me. And so that is my indication that I should stop. Question?
Does that mean that if you had a higher priority device at like a really high rate, or like sending data at a really high rate, it would just like overpower everything?
Yes, it would. Yes, it would. So it's something to be cautious of, because it is the case that the question was, does that imply that a high priority device could sort of hog the bus? And yes. And so you do have to be cautious about that. So that's how arbitration works on the CAN bus. We both just start talking, And every time we send a new bit of our arbitration field out, we check the bit that's on the bus to confirm that it matches the one that we put out. The moment that you attempt to put out a recessive bit, a 1, and you observe that the bus remains dominant, 0, then you know that you are not in control of the bus. If you get through the whole arbitration field, and every time you put a bit onto the bus, you've observed your bit appearing on the bus, then at the end of that arbitration field, you safely assume I am in control, because you know that every other device has the same length arbitration field and has a different name, a different arbitration value. So after having put all those bits out, all of the contention over control of the bus will have been resolved. Any questions about that? Yeah.
What was the message ID determine the devices? Because they have to be different, right?
How is the arbitration field determined for different devices? That's a great question. It would depend totally on your application. So in the event that your vehicle has, what would be a good example of this? Let's suppose you're building some sort of a system that requires very high-speed control in order to maintain like stability. I'm going to speculate. I don't know that the example that I'm about to use is a real example, but let's just suppose, for instance, that you're designing a Formula One vehicle, and you have a really tight control loop over one of the actuators in that Formula One vehicle to actually keep it stable, right, to the greatest extent that you can. It's probably the case that that control loop is closed around some collection of sensors that are organized around the F1 vehicle. So it's probably the case that you would assign those sensors low-value arbitration fields so that they get to win whenever they want to talk, because it's of high consequence that that sensor information get through the bus. On the other hand, I will bet that those F1 vehicles also have information flowing around the CAN bus that is of less, with less severe timing constraints. Maybe an example would be like tire temperature. I don't think it's probably the case that tire temperature is changing at, that you would need to update your knowledge of tire temperature at, say, 50 kilohertz, right? You could probably update your knowledge of that at a much slower rate. And so you might assign your tire temperature sensors arbitration fields that are lower priority, so that they'll communicate when they can, but in the event that the tire sensor and your IMU, or whatever it is that's maintaining your tight control loop, are trying to talk at the same time, your IMU is going to win. So it would depend on your application and your requirements. Any other questions about this? So why might this be popular for vehicles? Does anybody have any intuition for this? It's quite robust. It is quite robust. And furthermore, there's very little wiring here, right? There's essentially a single differential pair is the whole CAN bus. Every node on that CAN bus just plugs into that differential pair, right? And so it allows for you to use less harness, less wiring than you might have to use if you chose to move information around your vehicle using some kind of other protocol. And so it's handy in that it requires very little wiring. Now, of course, because it requires so much less wiring, that is the reason that the protocol here by which we actually send data is a bit more complicated than you might see on, for instance, SPI. SPI, the protocol is dead simple because there's a clock line, so we don't have to worry about any of this synchronization bit stuffing business because there's just a clock there. You just synchronize based on the clock. Furthermore, there's 2 data lines, right? And there's a chip select line. And so that spends a lot of GPIO, but as a consequence of having used that GPIO, we don't have to encode that kind of information into our packet in the way that we do here with CAN, right? So that's why the packet structure of this is a bit more complicated, because we have to solve all these synchronization and arbitration problems using the packet and to some extent the physical layer, right? We've designed this such that zeros win over ones, which was quite clever, really clever. So we have to design our physical layer to some extent in our packet structure in order to resolve these problems that are trivial in, say, SPI. But then as a consequence, we get way fewer wires than if every device in our car was an SPI device, which would require a chip select line going to every single one of it, right? Which would be very expensive and possibly error prone. Any thoughts about this? So when you're working with these things, it is often the case that you'll have a CAN transceiver, which is a little integrated circuit device that takes as an input its interface to, say, a microcontroller would be a TX and RX line, kind of similar to like a UART channel. But then on the other side of it, it's that transceiver that then interfaces with the CAN high, CAN low differential data lines. Okay. So if you'll indulge me, I'd like to talk a little bit about the PIO version of this, because what I want to talk about is how we can use PIO on the RP2040 to engineer all of these features that I just discussed, right? So we can engineer, in particular, this arbitration business in the PIO state machines. The idea being that we can set up a microcontroller program that allows for the user to specify, you know, an arbitration value, some data, compute a checksum, and then in the C code, stuff that packet and send the stuffed packet off to a PIO program. And the PIO program will autonomously, separately from the CPU, attempt to put that packet onto the bus. In the event that it encounters an arbitration collision, it will stop and try again at the appropriate time, and keep trying until it has successfully sent the packet, at which point it will alert the CPU that it has done so by way of an interrupt. So in effect, what I want to describe is how we can use PIO and DMA to implement a non-blocking CAN driver, a program that allows for us to specify a packet, toss it over to the PIO, carry on doing our other stuff, and trust that that PIO channel is going to get that packet sent when it can, based on these arbitration rules. I'm going to do my best to explain this because it's a bit of a challenging program to describe, but I think it's interesting, and so I'm going to try to describe it. So the whole system architecture looks like the following, and I'll start at this level of abstraction, and then I'd like to zoom into these PIO state machines and talk to these a bit more. This picture is describing the CAN transmitter. There's a separate picture further down that describes the CAN receiver. And in this particular implementation, the CAN transmitter and the CAN receiver live on two different cores of the RP2040. They use totally different PIO state machines and different DMA channels, which is to say that the CAN transmitter part of this and the CAN receiver part of this are completely independent. They are not aware of each other's existence. So how does the CAN transmitter work? Well, in the C code, as we'll look at here in just a moment, the user populates a number of different parameters for how much time must the bus be idle before we're allowed to send a packet, for instance. What is our arbitration value? What is our payload length? What is the value of our payload? We populate those values into, this particular application populates them into global variables or arrays, right? So we populate a bunch of different variables or a bunch of different arrays with the arbitration value for that particular transmission and with the payload. We then call a function that we'll look at the implementation of in just a moment here, but this function send packet, what it will do is on the CPU in C code, it will go through and compute the checksum over all of the information that we want to send. It'll then compose a packet based on all of these different fields and go through and bit stuff that packet So it's going to scan through the packet, and every time it encounters a sequence of 5 bits, 5 identical bits, it will insert an opposite polarity bit. So it stuffs the packet. Once the packet has been stuffed, send packet will start DMA channel 0, which shuffles the stuffed packet to this PIO state machine that we're about to look at in more detail, basically one piece at a time. So it'll send it over the arbitration, and then it'll send it over the rest of it. And the PIO state machine, as we'll see, is responsible for taking that packet and putting it onto the bus, making certain that it is not causing any arbitration collisions as it does so. So basically, it'll go through, put each bit of the arbitration field out onto the bus, check the value of the bus for each bit after it does so to make sure that it has one control of the bus, and then only in the event that it has one control, it will send the rest of the packet. In the event that it encounters a collision, it will stall, and it'll try again once it observes that the packet that the bus has been idle for this tx idle time parameter time, 3 bit times or so. Okay. So this is how this looks. The other reason I wanted to bring this up is I would love, in many of your lab reports, a common comment on those lab reports is a request for inclusion of a software architecture diagram. What I'm requesting when I ask for that is something kind of like this. A picture that shows all the stuff that composes your program, where it lives, and at a high level what it's doing. And so in the case of your final projects, for instance, a software architecture diagram might include a block for core 0, a block for core 1. Within each of those cores, there might be little blocks that indicate the threads that are on each of those, and a brief summary of what that thread is responsible for. You may also have blocks for interrupt service routines, and there may be labeled arrows that show mechanisms of communication between these various pieces of your program. Some of your software architecture diagrams may also include PIO state machines, may include DMA channels, may include external devices. But this is the kind of thing that I'm asking for when I'm asking for that. And by the way, it doesn't have to look exactly like this. I would just like for it to carry this kind of information. And so just in the event that there was any confusion about those comments on lab reports, it's this kind of thing that I'm asking for. Some illustration of what's happening where in your program. Okay, the receiver looks very different. The receiver interfaces with the CAN transceiver, and this is checking the bus, and as packets appear, by way of a DMA channel, it's shuffling each bit of that packet into a global array. Remember, that packet arrives stuffed. It arrives with those extra bit-stuffed bits in it. Once a full packet has been received, and by the way, we know that a full packet has been received once we encounter the end of frame indicator. That's how we know that's the end of that packet. It will call a function called attempt packet receive, which goes through and unbit stuffs that packet, computes the checksum over the received packet to make sure that there wasn't any error. And then it checks by way of one of these fields in the packet whether that particular packet was destined for receipt by itself, or if instead it's a packet for somebody else, in which case it ignores it, right? But it actually receives every packet, parses it, and then checks the fields to see whether or not it was meant for it to take some action with or not. And the PIO state machine causes for that to happen by way of an interrupt. So it receives a packet, triggers an interrupt. That interrupt will try to receive this packet, and in the event that it was a valid packet destined for receipt by that particular node, it semaphore signals a thread to go do something with it. Okay. But like I said, this lives totally independently from the receiver. Okay, so I thought it would be interesting just to take a peek at this PIO program that implements transmission. It's a difficult program to describe, but I think it's an interesting one, and I don't know, maybe you will too. The reason it's a difficult program to describe is it's highly nonlinear. It jumps around a lot because it has to jump around a lot in order to manage this arbitration. But it's divided. If you take a look at the program labels here, this attempts to describe the various sort of pieces that the various sort of pieces of this program. There's a standby section in which nothing is really happening. There's a section here that occurs every time the user attempts to send a packet. We enter this part of the program. In the event that the bus is idle, this is the section of the program that does that arbitration process that I just described, which we'll talk about, but that's where arbitration occurs. After arbitration, this is the section of the program that sends out the rest of the packet. And it knows when to stop sending the packet because it is counting the number of consecutive ones that it has sent. And when it counts 7 consecutive ones, it says, that must be the end of frame indicator. I must be done with this packet. So in other words, this PIO program does not know the length of the packet that it is sending. It finds the end of the packet based on that end of frame indicator. That was just a requirement for this project, for the particular application I was working on it for. Okay, so let's talk through how this works. So, we're sitting up here in standby, stalling on that pull. There does not exist yet anything in the TX FIFO to actually pull, and so this PIO program sits and blocks and waits there. When something appears, the first thing that will appear is going to be that arbitration field. 16 bits. It's going to be a 16-bit arbitration field. So as soon as we pass that pull, what we have pulled into the output shift register is the arbitration part of the packet. The next thing that happens is we copy that arbitration field from the output shift register to the Y scratch register. As we'll see, we do that copy so that we can remember it in the event that we have an arbitration collision and we need to start over. By storing the arbitration field in that Y scratch register, we have the ability to start over without somehow asking the C program to send us that again. We've remembered it locally in one of the scratch registers. So, okay, once we've received the arbitration field, the next responsibility of this program is to make certain that a sufficient amount of time has passed since the last packet so that it is allowed to attempt to send a new packet. There's a certain amount of delay time between packets that we enforce. And so that is what is occurring in these two stanzas, the reset OSR stanza and the spin wait stanza. The first thing that we do here is something that appears repetitive, but we only do this repetitive things because it's possible that we would jump back to this program label from elsewhere. We copy the contents of the Y scratch register into the output shift register. The output shift register now contains the arbitration field. We set the X scratch register to 0. What we then do is signal an interrupt flag, interrupt 1, and we wait for it to clear. When we do that, what we are signaling is a second, smaller PIO program down here. It's this program that is going to see if the CAN bus remains idle for a sufficient amount of time. So how does it do that? It waits to be signaled to take some action. It shifts 32 bits from the output shift register to X. There's an implicit auto pull there. What it is in fact pulling is the TX idle time that the user specifies. The user gets to enforce, here's how long I want for the bus to be idle before a subsequent packet can appear. That's what it's pulling there, measured in PIO cycle times. What it then does is go into this idle check, jump, pin, spin, wait. The pin that it is checking the polarity of there is the RX input pin of the CAN transceiver. It's effectively checking the state of the CAN bus. In the event that the pin is high, it jumps to this instruction, which decrements the X scratch register, stalls for a bit time, and then jumps straight back up there to check it again. So you could imagine that if the pin is high, the bus is idle, it's jumping from this jump to this jump to this jump to this jump, decrementing X as it does so, counting down the amount of time that it is supposed to make certain that the bus has remained idle. So there's two possible paths that this could take. Let's say the bus remains idle for the appropriate amount of time until ultimately X decrements to 0. Then what this will do is send interrupt 2 back to the original state machine. We'll look at that in just a moment and wait for it to clear. In the event that at any point here it detects that the bus has gone low, that indicates someone else sent a packet. It will reset the X scratch register, fall through to this jump instruction, and try again. And so it is polling the state of the CAN bus to make certain that it has remained high for a sufficient amount of time, and only after it has remained high for a sufficient amount of time, this interrupt gets sent back to the original one, up here. So you can see that after that interrupt wait 1, we have a wait 1 interrupt 2. That means send this interrupt, wait for it to clear, and wait for interrupt 2 to go high. When it goes high, clear it. So once we fall through that wait, we are in a position where we know that the bus has been idle for a sufficient amount of time for us to attempt a packet transmission. We do one final check just to make sure that nobody has started right before we start to send the message by way of this jump instruction. Jump pin 2 pins. In the event that pin is high, that means the bus is still idle, and we're going to jump down here and start attempting arbitration. In the event that pin is low, that means in the last PIO cycle time, somebody has started a transaction. We fall through to that second jump instruction, which moves us back up to the spin wait program label there, and we try again. But let's suppose that we fall through. Let's suppose that this remains true. The bus is still idle, so we are going to attempt to take control of the bus. We're going to do arbitration. The way that we do this is we jump to the 2 pins program label. We move. Remember, we've initialized X to 0 there, right? So right now the X scratch register has a value of 0. We take the value of the X scratch register and move it to the pins, put it on the bus. Remember, every packet starts with a start of frame indicator, which is a 0. So this is us putting that start of frame indicator out onto the bus. Put a 0 onto the bus. What we then do is hit this jump instruction. This jump instruction is taking 2 different actions based on whether or not we put a 1 onto the bus or a 0 onto the bus. We're always going to put data onto the bus in this part of the program through this X scratch register. In the event that we just put a 0 on the bus, we fall through this jump instruction because X is 0. And this is a jump under the condition that X is non-zero. In the event that we put a 1 onto the bus, X is 1, this jump condition is satisfied, we decrement it, we make it 0, and then we jump to the check collisions field here, which I'll go to in just a moment. But let's suppose that it's a 0 because the first bit that we put onto the bus is in fact a 0. We're going to hit this jump instruction. It's going to go, well, it was a 0. I don't need to do this jump. Falls through to a no-op. The reason for that no-op is just to make the 2 path lengths identical. The number of instructions associated with 1 and the number of instructions associated with a 0. We needed an extra 1, so we put a no-op in for the 0. We fall through the no-op to this jump where we check the condition that the output shift register is empty. In the event that the output shift register is not empty, we jump to the bit out instruction. Remember, the output shift register holds our arbitration field. So what we're really asking here is, have we put the whole arbitration field out onto the bus yet? The answer to that question after the first bit is, of course, no. And so we would jump up to the bit out instruction. We put another bit out onto the bus. Or I'm sorry, we copy 1 additional bit from the output shift register to the X scratch register. Fall through to this instruction that we've visited before. We take the contents of that X scratch register and put it to the pins. Let's suppose that this time it's a 1. So we put out the 0, and now we're putting out a 1. In the event that we've just put a 1 out on the bus, that means the X scratch register has a 1 in it. This jump condition is satisfied, and so we jump to the check collision program label. Remember, 1s are recessive. And so the way that we are doing arbitration here is every time we put a 1 onto the bus, we check the bus to see if there's a 1 there. If there's a 1 there, then we can maintain confidence that we are still in control of the bus. If we find a 0 there, it means that a device with higher priority than us has put a bit there, and we should stop. So what we do after having put a 1 onto the bus is we decrement x back to 0 and jump up to the check collision program label. Here, that jump pin, that is us checking the status of the bus. In the event that pin is 1, then we are still in control and we jump to next bit, right, where we visited before. Basically, we're going to go get the next bit of the arbitration field and try it again. In the event that pin is 0, that means we have lost arbitration. Somebody higher priority has put a 0 on the bus. In that case, we fall through that jump instruction and we do an unconditional jump back to the program label called reset output shift register. Reset output shift register lives up here, where we visited this before. We reset the value of the output shift register by copying the contents of the Y scratch register. That's where we stored the arbitration field back into the output shift register, and we go through that process again. So this is the mechanism by which the PIO state machine is enforcing that interesting arbitration capability that the CAN bus offers. It goes through, gets its arbitration field, puts it out 1 bit at a time. Every time it puts out a 1, it sees if a 1 appeared on the bus. If it did, it carries on. It keeps going until it has emptied its output shift register. In the event that it has lost, it keeps trying until it wins. By the way, Aiden, Edmund was asking why 16 bits on the transmission. I think it's for this reason. I think. Because I wanted the 16-bit arbitration value to appear as a single DMA transaction, if I remember correctly. Okay. Okay, so let's suppose we get through this whole thing, right? So we have 1 arbitration, which means we've emptied the output shift register. So we get finally, after our last bit of arbitration, to this instruction. This is now empty, so we fall through. The next thing that we do is send the message. We set the Y scratch register. Remember, this previously held our arbitration value. Now it's going to hold a different value. That's a parameter, not present here, but if you look at the program, it's present. That recessive end of frame threshold, that is the number of sequential 1s that we will be required to count to indicate the end of a frame, the end of a packet. So we're initializing the Y scratch register to hold the number of successive 1s that indicate the end of the packet. I think it's 7. But okay, then we fall through. Now we're going to do another pull. Last time we did a pull, we were pulling in the arbitration value. This time, we're pulling in the stuffed packet, 16 bits at a time. Okay? So this is the first 16 bits that we're going to put out onto the bus. We fall through to another bit out program label. We call an out instruction to move 1 bit from the output shift register to the X scratch register. We move that bit to the pins, and then we take 2 different actions based on whether or not that bit was a 0 or a 1. In the event that that bit was a 0, we fall through this jump instruction and we reset the Y scratch register back to its default value. In the event that that was a 1, we jump to the recessive out program label, decrement the Y scratch register until it's 0, right? And then we jump to the next bit again, where we check whether or not the output shift register is empty. Have we emptied that last 16 bits that we were supposed to send? In the event that we have not, we jump to this path correction, which again is just enforcing the same number of instruction times based on 1s going out and 0s going out. This is an unconditional jump back to another bit out with a delay to enforce that this takes the same amount of time whether you're sending a 1 or a 0. And we go through this process again. So in short, in the event that we're sending 1s, every time we send a 1, we're decrementing the Y scratch register because we're counting the number of successive 1s that we've sent. In the event that we send a 0, we reset the Y scratch register so that we start counting from that threshold again. This is the mechanism by which we are looking for the end of the packet. And we're going to keep sending stuff out, keep pulling stuff in until we count recessive EOF threshold number of 1s in succession. Once we do, we interpret that as being the end of the packet and fall through to this transaction complete instruction label, program label. We send an interrupt. This one is consumed by the CPU. This is the interrupt that gets thrown on the processor to indicate, hey, I finished sending that packet that you sent me. So the application code builds the packet, shoves it off to the DMA channels that are going to exchange it with the PIO state machines. This all occurs separate from the CPU. And then it will signal back to the CPU when it has finished sending that packet. By the way, there's a similar program down here for receive that we don't have time to talk through. I wanted to show you this because I think it'd be really hard to do with this without PIO. It's a really cool, I think, example of PIO programs. And you know, I have to say, well, do I want to say this or not? I like this program a lot. I've written a lot of programs. I don't often feel one way or another way about the programs that I write. They're all just kind of interesting. Or, you know, I sort of love them all equally, I guess. But this one, I just really, really like because this transmit PIO state machine, right? It's composed of what we just talked through and this idle check. Those are two state machines that live on the same PIO block. If you count up all the instructions that compose these two things, there's 32 exactly. And I don't think you can take one away. It took like a month to figure out how to fit this into 32 instructions. Maybe you could take another one out. Maybe it can be a little bit more optimized, but it's not obvious to me how to do that. And so I have to say, I think these 32 instructions, if I had to point, if someone told me to point to the program that like they're most sort of proud of, most like, these 32 instructions. I love this program. And so I wanted to share it with you as well. Okay, I'm going to be in lab this afternoon. Of course, I'll see many of you then. I'll see the rest of you Wednesday.